Welcome to this lecture about air handling units, AHU. They are used to bring ventilation air to a comfortable state. In some buildings, they are also the only heating or cooling system present, while in others, they work as an addition to other heating and cooling systems. In another course, you learned about the relationship between relative humidity and air temperature when it comes to comfort. The inner zone is deemed to be comfortable and is followed by a zone where it is still comfortable, afterward the discomfort becomes high. This diagram is in principle only valid for an air-conditioned office room. We can draw this diagram in a Molière carte, which gives this. The aim of handling air is to bring it in the comfortable zone, by preference the inner one. This is done just by heating or cooling air at room level. We will study that in another part of this course. But in larger and a bit more sophisticated buildings, this is done by using air handling units like these ones. They can be very large depending on the airflow rates to be handled. Such an air handling unit consists of different components. In its most extensive design, an AHU looks like this. Outside air is supplied on the left. If mechanical supply and exhaust ventilation is applied, the air from the rooms is exhausted through a return pipe here, possibly combined with a recirculation and heat exchanger unit. Note the filters at the air inlets. We then have a first heater indicated with a plus. The heat is provided by an electrical heater in the unit or through a heat exchanger by any of the heat generation systems we studied in another course: boiler, heat pump, geothermal heat, waste heat, etc. Then there is a humidifier, either an adiabatic one using water droplets or a steam one. Then comes a cooling system indicated by a minus. The cold is provided through a heat exchanger by one of the cooling systems described in the course Energy Supply for Buildings, a chiller or geothermal cold. And you see a second heater here after the cooler. And finally there is a fan pushing the conditioned air to the rooms. In practice, it may look like this. You see here one of the air handling units in the building I am working in. The white box in the middle is the unit itself with some of the elements we just described hidden in the unit. You see on the foreground the pipe with return air from the rooms, which is polluted air, indicated by the brown arrows. In the unit it goes through a heat exchanger, and at the other side it flows to the outside of the building through the exhaust air pipe. The blue arrows show the path of the outside air, which undergoes some of the processes described previously and then is led to the living zone. In many systems, the air is led directly to rooms, but in my building it is simply supplied to the corridor and from there goes naturally to the rooms, which are in slight under pressure because there is a fan in the return pipe sucking the air out. Ventilation systems can be divided into four types. The completely natural ones on the left through windows or grills. Second, the ones with an exhaust ventilator pushing the air out of the building while the supply air comes naturally in. Third, the ones with mechanical supply where the air is pushed inside the building and then flows away through window openings and cracks. And fourth, the ones with mechanical supply and exhaust, generally equipped with a heat recovery heat exchanger. The air handling unit we have just described and the pictures we saw are for the last of these systems with both mechanical and supply ventilation. However, it happens very often that there is only mechanical supply, the third system. In that case, the air handling unit, if any, will look like this one. There is no return pipe, of course. Let's look first at the case when there is a return pipe, exhausting the polluted air from the rooms. In general, during the heating season, this air is warmer than the outdoor air, giving possibilities for heat recovery. During the cooling season, it may be that the return air is colder than the supply air, and heat recovery, in fact cold recovery, can then also be applied. In some systems, Recirculation is applied, meaning that a part of the return air is mixed with the clean outdoor supply air. This is a cheap way of preheating or pre-cooling the supply air, but is only responsible when the flow rate of return air being mixed is very small in comparison with the flow rate of the outside air. Otherwise, the concentration of indoor pollutants could increase a lot. Note also that at both the inlets of supply and return air, filters are placed to remove dust particles, meaning that these filters must be cleaned and replaced regularly and kept dry, otherwise they will become a source of indoor air pollution, as you can learn in the MOOC Health and Comfort in Buildings. Let's look into more details at the mixing section. A is the incoming air, B is the return air from the rooms, C is the air after mixing. People produce a lot of humidity. During the heating season, it is likely that the outdoor air is much drier than the indoor one, so the air after mixing, C, will be warmer but also more humid. This is the process you can see in the Mollier diagram. If the supply air is at conditions A with mass flow rate MA and the return air is at conditions B with mass flow rate MB, after mixing, the air will be at conditions C. In a cooling situation, in a hot and humid climate, it is on the contrary likely that the return air is drier than the outdoor air because it is air-conditioned to low humidity, by which point A would be located, for instance, here, and the mixing process would go along this line. Regardless of the presence of a mixing section, heat recovery can be applied. This is done in a heat exchanger. If the outside air can be heated by the return air, which happens during cold weather, the process is a heating one, as shown in the Mollier diagram. If the outside air can be cooled by the return air, which happens during hot weather, the process is a cooling one, like here. In such a heat exchanger, the supply air and the return air are not in contact. There is only heat exchange, no mixing. This is therefore much cleaner. The supply air cannot be polluted by the return one. Such a heat exchanger could look like this cross-flow heat exchanger. This is a heating example. The two flows of air are separated by plates and exchange heat through the surface area of the plates. To allow for heat exchange, there must be a temperature difference large enough between both flows. Generally, it will be between 2 degrees for very efficient heat exchangers and 10 degrees for less efficient ones. Instead of using a conventional heat exchanger, it is also possible to use a thermal wheel, which is a rotating heat exchanger placed between the return air pipe below and the supply air duct above. The wheel is an aluminum structure with a lot of surface, just like in a beehive. Let's take an example in cooling mode. The wheel rotates very slowly in such a way the aluminum of the wheel has time to be cooled by the return air passing horizontally below through the beehives. When it arrives in the upper part, the wheel starts to be heated by the warm outdoor supply air at point 1 and cools this way air to point 2. It would work similarly in heating mode. This thermal wheel have generally a high efficiency. However, air can leak through the wheel between the return duct and the supply one, by which some mixing and therefore air contamination can take place. It is much less airtight than the heat exchanger we saw in the previous slide. It is also possible to place adsorption material like silica gel in the beehives, enabling drying of humid air by adsorption, which is an adiabatic process leading to drier and hotter air. During drying, latent heat of evaporation of water vapor is released in the air, increasing its temperature. This can be used in two different ways. First, to dehumidify warm and humid supply air. That's the configuration that you see here, where outdoor air at 22 degrees and 90% relative humidity is dried to 60% humidity at the expense of a temperature increase to 26 degrees. See Mollier diagram on the right. A second possibility is to increase the heat recovery in a heating situation. If the return air is dehumidified, its temperature increases a lot and more heat can be recovered by the cold outdoor supply air. This is used in buildings with high occupancy where the return air is generally quite humid. Temperature levels could then be like the ones in brown, where by dehumidifying the return air from 60 to 45%, its temperature is increased to 27 degrees, allowing to heat outdoor air, in our example from 17 to 22 degrees. This works as a cycle, and once the silica gel is saturated, it has to be regenerated by circulating air through it at high temperatures above 100 degrees, by which energy is used. This is called the desorption process and costs energy. That can be calculated by taking the latent heat of evaporation of water times the total mass of water that have been absorbed by the silica gel. Additionally, it may be that pollutants are also absorbed in the wheel and transported to the supply air. Let's look now at the processes in the supply air and start with the heating mode. In the heating mode, the cooler is off. Only the first heater, the humidifier, and the second heater are used if needed. If solely heating is desired, the first heater is switched on and the humidification is bypassed. You see the process in the Mollier diagram going from 2 to 3. As for the heater, it can be an electrical heater placed directly in the heating compartment or a heat exchanger connected to a heat generation system like a boiler, heat pump, district heating, geothermal heat, etc. Such a heat exchanger may look like this one. If humidification is needed, which would be the case in this example as the humidity of air is very low, a adiabatic humidifier can be used, by which the air cools down a lot to 0.4 and needs to be reheated by the second heater to 0.6. The second heater is also an electrical one or is connected to the central heating system. Adiabatic humidifiers, you see one here, are very energy efficient. They use almost no energy, just a bit for the pump. However, they are prone to being polluted by the Legionella bacteria, causing pneumonia when inhaled. The Legionella bacteria grows by preference in water at temperatures between 15 and 50 degrees. The water tank should be therefore regularly chemically or physically disinfected or heated once a week at a temperature above 60 degrees in order to kill the bacteria. That's why preference is often given to steam humidification. A second solution to humidify is to use a steam humidifier. You see now that steam is injected into the humidifier. Part of the steam is absorbed by the air, but the excess part condenses again and is brought back to the steam boiler to be evaporated again. The steam has a temperature above 100 degrees and is produced in the tank here below, which therefore needs heat. Here too, an electrical resistance placed in the boiler can be used, or heat can come from a central heating system. Heat pumps have too low temperatures to make steam, so a boiler will be used, or industrial waste heat, or heat from a high temperature district heating. Steam humidification in the Mollier diagram goes like that. Depending on the temperature of the steam, the slope of the arrow may be higher or lower and is tuned in such a way that 0.4 and 0.6 are identical, so the second heater is not needed. Energy is needed for the steam but not for the second heater, and in total this system uses as much energy as the adiabatic humidification one. However, it needs high temperature, but it is much safer from the point of view of Legionella contamination. At 100 degrees, the Legionella bacteria cannot survive. What happens now in cooling mode? Well, the first heater and the humidifier are both switched off, and the state of air at point 4 is the same as at point 2. For the cooling of the air, chilled water is needed and comes from a chiller, also called a cooling machine, and which is exactly the same as a heat pump, as you can learn in the course Energy Supply for Buildings. Alternatively, it can also be delivered by geothermal cold or cold surface water like sea or lakes. The heat exchanger itself is of the same type as the one we described for heating. In the Mollier diagram, the process of cooling looks like this and results in colder air, but also in much more humid air. The relative humidity has increased up to 85%, which is high. To dehumidify the air, a solution is to go on with cooling along the saturation line to the dew point 5, by which the water vapor in air condenses. The air becomes drier and the droplets must be drained away. So, in coolers, there must be a drain. Look on the picture left. At point 5, we have now much too cold air that must be heated to the right temperature using the second heater. This brings us to point 6. To summarize, when cooling above the saturation line, the second heater is not needed. When cooling goes along the saturation line, air is dehumidified and in general cooled too deep, by which the second heater is needed, which is also the reason why there are 2 heaters in air handling units. Summarizing, you are now aware of all processes taking place in an air handling unit. You know which components are present in which order, and you can draw the processes in the Mollier diagram, which is very helpful for the design of such AHUs. We discussed that if there is a return pipe, recirculation and heat exchange may be applied. We also discussed dehumidification by adsorption with thermal wheels. We then focused on the handling of the supply air and looked at heating, humidification, reheating, adiabatic and steam humidification, and finally at cooling, dehumidification and reheating. Note that this lecture was about the most extended air handling units. Of course, there are smaller ones, in which only a part of the processes is done. For instance, in homes in Europe, generally only the heat recovery part is done. In moderate climates, it may be that only the heating part is present and that humidification is not applied. In hot and humid countries, only the cooler and the second heater will be present. Thank you for listening and have a good day. Goodbye.